Hello and welcome back once again to this lecture series on aluminum-based alloys and metal matrix composites.
All right, so we have seen different forms of dynamic recrystallization. Primarily, there are three forms of it: discontinuous, continuous, and geometric. So the DDRX and CDRX process we have already discussed. So next in line is the geometric dynamic recrystallization, or GDRX. So why it is called geometric, that will be clear in a moment as we discuss the mechanism of this particular phenomenon. So here also it starts with the dislocation rearrangement into subgrain boundaries. So the dynamic recovery process, or the DRV, will again come into play over here. And the GDRX generally occurs in materials with high stacking fault energy. Which are deformed at low strain rates. Yeah, so to talk about the mechanism, as I said, the subgrains are formed after a critical strain. And this occurs near the grain boundaries, near the original grain boundaries. And as we have seen before, due to the occurrence of this DRB and formation of these subgrains along the original grain boundaries, serrations develop. And now how these grain boundaries will behave and how the new grains will form, that would depend on the kind of deformation given to the material and how the grains change with respect to that deformation. So how the shape of the grains will change, that will matter in this case. So from there you can understand as to why it is called geometric, because how the grains will change their geometry as the deformation is continued after the serrations form, that would decide how the new grains will form. Okay. So in this case, as you deform the material and the serrations form, what could happen? One of the possibilities is that the grains can thin down, particularly if we are talking about a deformation process in which it is deformed in a directional manner. For example, in rolling, the deformation is in a particular direction, right? So in such kind of a deformation, the grains can actually thin down as they get elongated, right? So the process, if you see as to how the grains change their shape and how they will encounter with the serrations formed at the grain boundaries, that you can see from this particular diagram over here. So here this is in the beginning, the formation of the serrations by the DRB process. And these are shown by a different color. The blue color that you see, right, those are the serrations. Right, so as the material is subjected to more deformation, the grains can thin down, as you could see from the second figure over here. While the size of the subgrains remains constant, right? Although the grain size is changing, the grain shape is changing, but the subgrains remain constant, okay? So eventually the size of the serrations will be comparable to the grain thickness as it is deformed more and more. So that's what you can see over here. This will occur when the grain is typically having a size which is equivalent to few subgrains, okay? So under those kind of conditions, when the grains thin down to that extent, the serrations become comparable to size of the grain or the thickness of the grain, and eventually these serrations will impinge upon each other, and the equiaxed grains, the new equiaxed grains can pinch off due to that process, okay? So if I want to show you that if I simply remove these grains from here, from this particular diagram, from the third one, you would realize what I'm trying to say here. Let me see if I can remove this. Right, so I have just removed these grains and I have left behind only the serrations over here. So you can see, as the serrations become comparable to the thickness of the grain, you can see they are approaching to each other and eventually they will touch each other, they will impinge on each other, something like this. Right, so as the serrations impinge on each other, from these points, equiaxed grains can pinch off. Right, so this is how the new equiaxed grains will be generated due to a change in the shape of the grains as a result of the deformation which is given to the material, right? So now you can realize as to why it is called geometric dynamic recrystallization. All right, so one thing you would have realized by now in all these dynamic recrystallization mechanisms, The new grains which are forming are actually not only recrystallized, but they are also finer in size, right? In every mechanisms that we have discussed, whether it is DDRX, CDRX, or the GDRX, we have seen the new grains which are forming are equiaxed finer grains, right? So it also tells you that these kind of mechanisms are associated with grain refinement also, right? Because as I said, the new grains which are forming are finer in size, right? So therefore, we may have to revisit this topic again when we talk about the grain refinement process. And this can particularly happen when the grain refinement is done in the solid state by deforming the material at higher temperature, right? So under those conditions of high temperature, high strain, in a particular strain rate, these forms of dynamic recrystallization can operate and lead to formation of fine grains, right? So we'll talk about this in relation to the grain refinement process when we actually talk about the grain refinement methods. And in fact, that is going to be our next topic with regard to the strengthening mechanisms that we have been talking about. So far, we have talked about several of these mechanisms, starting from the solid solution hardening. Then we talked about precipitation hardening. And after that, we also covered the strain hardening process. And then we were talking about this recrystallization process with regard to the strain hardening, right? But while talking about this, we have also realized that the dynamic recrystallization process is also related to grain refinement, right? So grain refinement is the next topic that we are going to discuss with respect to the strengthening mechanisms in aluminium alloys. You would have already seen this before, particularly this Hall-Petch relationship that we all talk about whenever the grain refinement comes into picture. This tells you that as the grain size is decreased, the strength increases. As it is proportional to the reciprocal of the square root of grain size, okay? But we are going to talk about this phenomena into little more depth as to what exactly happens, which ultimately leads to an increase in the strength, okay? So while talking about those mechanisms, we will in fact prove this equation, we will deduce this as we go on discussing about the mechanisms of grain refinement strengthening, okay? But before that, let us define the different parameters that we have in this particular equation. So here sigma is the yield strength of the material. Sigma naught is a parameter which is known as friction stress that represents the overall resistance of the crystal lattice to dislocation movement. K is known as locking parameter, which represents the relative hardening contribution of the grain boundaries. And D, of course, is the grain size. So you can see from here, as the grain size is decreased, the strength increases. And in terms of the dislocation mechanism, if you look at as to how exactly that happens, the grain boundaries act as the obstacle to dislocation motion. Which means if you have more number of grain boundaries, there will be more obstacles to the motion of dislocations and the strength will increase. Okay. So what happens when you refine the grain size or decrease the grain size? You basically increase the grain boundary area per unit volume. So therefore, it provides more resistance to the movement of dislocations, and as a result of that, the strength increases. Okay, so that is how, if you want to look at physically as to what is the physical significance of this particular equation, that is how you can explain it in terms of how the grain boundaries interact with the dislocations, right? But as I said before, we are going to look at little more depth here as to how that interaction happens, and from that, we can actually derive this Hall-Petch relationship. So in order to do that, we need to consider some of the theories which were proposed to explain this phenomenon of grain refinement strengthening, particularly with regard to this Hall-Petch relationship. And one of them talks about pile-up of dislocations at the grain boundaries. So as I said, dislocations will be obstructed by the grain boundaries, and as that happens, the dislocations will pile up as they encounter the grain boundaries. Okay. So this theory is proposed based upon the dislocation pile up at the grain boundaries. And this was proposed by Cottrell and later on it was also expanded by these three people, SLB, Frank and Navarro. So with the help of this dislocation pile-up theory which was proposed by Cottrell, SLB, Frank, Navarro actually took it up to derive the Hall-Petch relationship. So let's say we are talking about a grain boundary here and the pile-up of dislocations at the boundary. Here is the grain boundary, and dislocations have piled up at the grain boundary, and L is the pile up length. So let's say there are n number of dislocations in the pile up. And n can be given as follows. Tau s is the average resolved shear stress for moving the dislocations, right? And the other parameters are already known. G is the shear modulus, L is the length of the pile up, and B is the Burgers vector. So you can say that a pile up of n dislocations is equivalent to a dislocation of strength NB. And therefore, the stress at the tip of the pile up is NB into tau s, because tau s is the shear stress which is needed to move one dislocation, right? So if you have this many dislocations or a dislocation of this strength, the stress which will be developed at the tip of the pile up will be this, okay? And for a dislocation source at the center of a grain of diameter d, n will be given as this, and from here we can actually derive a parameter called the critical shear stress, which is the stress needed for the dislocations to move over to the next grain. So if we define that as tau c, dislocations can move over to the next grain only when tau s reaches this critical stress tau c, okay? So therefore tau c can be written as equal to n into tau s. And if we replace n here from the previous equation that we have for n, we would get tau c as and tau s is nothing but the applied stress minus the resistance of the lattice to the dislocation movement. So if tau I be that lattice resistance, then tau S can be written as tau minus tau I, where tau is the applied shear stress, and therefore tau C will be given as which can be also rewritten as where K prime will be given by this with all other parameters that you have over here. And now if you replace the shear stress tau by the principal stress sigma, we will get to the Hall-Petch relationship. Right? So this is how, with the help of the dislocation pile-up theory, the Hall-Petch relationship can be derived.
And with that, we come to the end of this lecture. Thank you for your attention.